How do I calculate delta T? Final minus initial. So equals final minus initial. All right. And is that final minus initial? Oh, I did mean minus. Okay, so this is going to be fine. That did look a little small. Final minus initial. 0.214. Okay. Now, for the standard run, okay, if you look at the manual for your solution calorimeter, it tells you what the formula is for the Q, the known Q. Remember, when you do a standard run, you know what Q to expect. So the formula is given in your manual, in the user's manual for your calorimeter as mass of trace in grams times parenthesis 58.737 plus 0.3423 times 25 minus T mean. Let's examine what this formula means. Basically, it's saying if your mean temperature was 25 degrees, this one just cancels out, and you just have whatever mass of trace is that times 58.737 joules per gram. Okay, I'm in calories. Okay, so traditionally these things were done when calorie was more in use. So this will give you the number in calories. It should be negative because this is an exothermic reaction. So the manual actually doesn't put that negative in, but let's go ahead and put it in because we know that delta H should be negative. So my formula here will be equals, let me see, let me make it a little smaller, equals mass of trace. Where's my mass of trace? This one? Oh, I put a negative, minus the mass of trace times parenthesis 58.737 calories plus 0.3423. So this second part right here is basically a correction when the temperature is not at 25, okay, degrees Celsius. So times 0.3423 times parenthesis 25 minus the mean temperature. Okay, close parenthesis and then close parenthesis one more time, and that gives you calories. So what would that be in joules? How do you convert calories to joules? Equals calories times 4.184 joules per calorie. That's your conversion factor. All right. What's your calorimeter constant? That's key capacity of the calorimeter and its contents. Well, again, basic equation for calorimetry, Q is equal to minus C delta T, right? What you call the heat of reaction is the amount of heat that has to flow to reverse the temperature change that you observe. So, and you just multiply the temperature change for the reverse process by the heat capacity of your calorimeter and its content. So C will just be minus Q over delta T. So it's joules per Kelvin. All right. So let's go ahead and put that in. What's my formula right here? Equals minus Q, okay, divided by delta T, which is this one right here, 588 joules per Kelvin. How did you get joules again? Is it multiplied by 4.184 joules per calorie. A calorie is 4.184 joules. That's a thermochemical calorie. Okay. The calorie that you may have encountered in physics is the original conversion, which is 4.186. All right. So what was our hydrate for our unknown run? Magnesium sulfate, heptahydrate, so MgSO4.7H2O. Okay. Now, if you want to format this, instead of a dot, you can put like a bullet. You can search the internet for the code for a bullet and copy and paste there. But that's fine. You can just use a period there. What's the mass of your sample? Let me use, whose data should I use? Okay, Jaslyn, what's your mass of sample? 2.4576. 2.4576. So this is Jaslyn's number. 4576. Okay. What's the molar mass of magnesium sulfate heptahydrate? 246.5. Okay. Grams per mole. Let's put one more sig fig because we got 5 sig figs in our mass. It's 246.50. 0.50. That's very fine. Molar mass of magnesium sulfate heptahydrate.
If you just look up MgSO4, it pulls up the heptahydrate.
Google usually. That's MgSO4. That's 7H2O. Google usually gives me right away what the molar mass is. Oh, right here, 246.4746. 4746. So 246.4746. Okay. Moles of sample would be how much? Mass over molar mass. So grams divided by molar mass. Okay. And make sure you round all of these off to the correct number of sig figs. Okay. So initial temperature is determined from the graph. Jaslyn's data. 384. Final temperature. 0.068. You can just follow along with my numbers for now. You can change it later. And then 23.185. Change it later with your actual data. So our delta T would be equals final minus initial. And note that our delta T in this case is negative. Why is it negative? Temperature drop, you have an endothermic reaction, right? So this is an endothermic reaction. If you want to put a formula here, you could. You can say if this number before is less than 0, then the answer is endothermic, comma, otherwise it's exothermic. Oops. Oh, I have to put an if, and it says endothermic. Okay. If the number delta T is negative, it's an endothermic reaction. If delta T is positive, it's an exothermic reaction. All right, so what's the C from the standard run? It's just equal to what we calculated previously, which is this number right here, B12. So that's your C. All right. Is that a reasonable C? How many mL of water did we have? 100, right? Approximately 100 times 4.184. 418 just for the water alone. Everything else in that calorimeter would be account for the difference. Okay. So what's Q for this reaction, this unknown reaction that you did? It's just minus C. So for your unknown run, Q is just minus C times delta T. So what we put here is equal. This is going to be equal to minus C times your delta T, which is this one. And if it's an endothermic reaction, it should be a positive number, 186 joules. Okay. What is it per mole? What should I do? Divide by the moles. This one divided by the moles. And it's asking for it in kilojoules, so I have to divide this by 1,000 to change it to kilojoules. 18.66 kilojoules per mole. This one? Whatever Q you have, divide by the actual moles of your sample. That gives you joules per mole. And then divide by 1,000 to give you kilojoules per mole. right?
Can I see the formula for the one underneath in the framework?
This one?
Oh, okay.
That's just the heat capacity of your calorimeter and constants. That's called the calorimeter constant.
And then the joules?
Huh? And then this one?
Yeah.
Q is just minus C times delta T. So this is minus C, which is B25 times delta T, which is B23. All right, so now let's determine the standard enthalpy of formation of your hydrate. Okay, so your formula for your anhydrous salt is MgSO4. That's the anhydrous salt. We can look it up. Where do we look it up? So a good source for the ions would be the CODATA website. Okay. So first of all, if I want to calculate the delta H formation of the hydrate, okay, here's a reaction. Let me see. Determine the enthalpy of dissolution of the anhydrous salt first. Let's do first the enthalpy of hydration, the enthalpy of dissolution of the anhydrous salt. So first of all, let's do this one. Magnesium sulfate solid. Let's say you want to get magnesium ions aqueous plus sulfate ions aqueous. Okay, let's get the delta H for that one first. Remember, for our experiment, this is the delta H we got from our experiment is magnesium sulfate heptahydrate gives you magnesium ions plus sulfate ions plus 7 waters. Okay, so this is the experimental value that we got. Okay, what we want to try to do is we'll try to figure out if we can determine the delta H formation of this. So let's start off with just this reaction first. Just the anhydrous salt, dissolve it in water. So what would we do? So let me rewrite that. If I want magnesium sulfate, aqueous, solid, gives me magnesium ions aqueous plus sulfate ions aqueous. Okay, and delta H for that would be equal to, for that reaction is equal, so it's R right here, is delta H formation of magnesium ion plus delta H formation of sulfate ions minus delta H formation of magnesium sulfate solid. Okay, so let's look these numbers up. What do we have? The anhydrous salt, where would we find it? Where would we find the aqueous solution? So let's do, am I recording this? Yeah. Okay, so let's go to the CODATA website. Okay, so what numbers can we find here? Let's see if we can find what we need here. Magnesium ions in solution, right there. In aqueous solution, magnesium ions have a delta H formation of minus 467 plus or minus 0.6. Is that delta H formation? Yeah, delta H formation. The second column, right? The next column right here is entropy. Okay, so you want delta H formation. So magnesium sulfate, magnesium ions would be minus 467.06. Okay, so this is magnesium ions. Your cation ion is magnesium, right? minus 467.06. What's our source? This website right here. So for the cation, this is our source. Okay. Minus 467.0 plus or minus, okay, 0.6. Okay. Minus 467.0. What's the formula for the anion? So your cation is, let's edit this, it's magnesium plus 2, right? Mg2 plus. Okay. And our anion is sulfate, so SO4 2 minus. If you want to superscript that, that's fine too. So what's the standard enthalpy of sulfate ion? Let's look for sulfur right here. Sulfate ion aqueous is minus 909.34. Okay. So same source basically. Minus 909.34. Okay, where can we find magnesium sulfate? It's not here. So let's try webbook.nisc.gov. Chemistry webbook. Let's do a search. Formula. MgSO4. Condensed phase data. Reaction data maybe. And let's see. There's magnesium sulfate. We got lucky. And there it is. So do a screenshot of that. Let's do a snip. Where's the Windows accessory snipping tool? So you have to use snip and sketch on yours. This computer hasn't been updated. So this one right here. This is magnesium sulfate solid. Copy that, put that on your Excel. For magnesium sulfate, I'll put it right here, right next to where I'm going to use it. So it's going to be minus 1261.79. Minus 1261.79. Is that what I have? If you want to take screenshots of the other one too, that's fine. Might as well do that. What was that other one? And the CoData website, magnesium ions. So let me take a screenshot of that. Right there. Okay. And it's 467. Copy that. I'm just going to put that over here. The magnesium ion, I'll put it here. And then where's the other one? Sulfate. Let's take a screenshot of the sulfate. Right there. Edit, copy. And let's put the sulfate over here. Oops. Sulfate's right there. Okay. So I've got all my screenshots to support my numbers. Okay. So how many moles of cation do I have in my anhydrous salt? In 1 mole of magnesium sulfate, I have 1 mole of magnesium, and I have 1 mole of anion, 1 mole of sulfate, right? So the balance equation, we have 1 mole of magnesium, 1 mole of sulfate. So this should be 1 times the value per mole. So this is 1 mole times the value per mole, 1 mole times the value per mole, minus 1 mole times the value per mole. This is all 1. Okay. So What are the numbers that we have? Call them out for me. Magnesium sulfate was how much? Negative 1261 kilojoules per mole. So you can see moles cancel out. Plus 1 mole of sulfate. What's the value for sulfate? -909.3 kilojoules per mole. Okay, magnesium ion is 1261. Okay. Negative 467 kilojoules per mole. So moles cancel out. And then minus the value for magnesium sulfate itself, 1 mole times, what is it for magnesium sulfate? 1261.79 kilojoules per mole. And so mole cancels out as well. So that gives you the delta H for this reaction. So in other words, if you did this experiment using the anhydrous magnesium sulfate, how can you make anhydrous magnesium sulfate from what you had in the lab? Remember the experiment you did freshman chemistry? You heat up your magnesium sulfate heptahydrate, the residue would be the anhydrous. So if you took that residue and did the run for that residue in your calorimetry, you would be able to get this number. Okay. So anyway, on a per mole basis. So anyway, how do we calculate this? What's the standard enthalpy of dissolution of the anhydrous salt? This is the dissolution of the anhydrous salt. This is the standard enthalpy for that. And what is it? Based on what the numbers we have entered here. So this is going to be, delta H formation of the products. What are the products? Magnesium ion times 1, right? Times 1 mole of cation plus 1 mole of anion, the value for the anion times 1 mole of the anion, minus the value for the anhydrous salt itself times 1. Okay, and this would be your delta H of dissolution of the anhydrous salt. Okay. So we're still good? Huh? You're getting an error? Make sure these don't have any letters in them. It's all numbers. So it's cation. So 909 B34 minus 467 times 1 mole of cation plus anion is minus 909 times 1 mole of anion minus 1 mole of the anhydrous. Okay, so going back now to our equations, I have this magnesium sulfate solid yields magnesium ions plus sulfate ions aqueous. Delta H for this reaction is how much? We just solved it. We just negative 114.55 kilojoules. Now from our experiment, so this is literature, right? Our experiment, we have magnesium sulfate. Let me write this in different color. Magnesium sulfate heptahydrate solid yields magnesium ions plus sulfate ions plus 7 H2O liquid. And the delta H for this from our experiment was how much? We calculated that earlier. Okay. Using Jaslyn's data, it's 18.66 kilojoules per mole. You're going to have to use your own data for that one. So 18.66 per mole. Positive 18.66 kilojoules. All right. What are we looking for? We're looking for the enthalpy of dehydration of the hydrate. What do we mean by dehydration of the hydrate? I want, the reaction I want is this one. Magnesium sulfate, dot 7H2O, solid yields magnesium sulfate solid plus 7H2O liquid. What's the delta H for this reaction? How do I get the delta H for this reaction? From the two that I already know. Hess's law. I want this as a reactant, so let's call this reaction 1, reaction 2. I flip the first one, right? So, and I keep the second one as is. So this means this is just going to be delta H for reaction 2 as is plus the negative of the delta H for reaction 1. Hess's law, right? So this is reaction 2 plus flip reaction 1. Okay? So what's my, how do I enter that formula right here? Equal to the value for reaction 2. Oh, that's not 2. 2 is this one, right? Minus, flip the value for reaction 1. So plus the negative of the value for negative 1, for reaction 1. And this is our answer right here. So that's the standard enthalpy of dehydration of the hydrate.
Can I see 40? Because I got 115. Like 114.
This one? Check your number of decimal places. And if you're already using your data, you may get something slightly different. But you should get close to that number, right? Because you're all using the same unknown. Okay. Now, the next step is to determine the enthalpy of formation of the hydrate. And we can do that because we now know, so we already know this time, so we just figured out magnesium sulfate heptahydrate solid yields magnesium sulfate solid plus 7H2O liquid. What did we say the delta H for this was? Using my number here, it's my 133, right? I'm just going to put 133. You can, because you can do this calculation in Excel anyway. So 133 kilojoules. Does that make sense though? Removal of water from your hydrate, should that be a positive delta H? Do you need to produce, does it need to absorb heat to get the water to leave? Okay, so that should be an endothermic, so you know it's a reasonable answer, at least algebraically. Now, I can look this up, right? Delta H formation of liquid water, we did that last time when we did the bomb calorimetry. I can look this up. We actually looked this up already. What is this? Magnesium sulfate is how much? Negative 1261.79, right? Kilojoules per mole. And what's the value for water? Let's look it up from web book. You remember the number? 285, was it? Let's look it up. Webbook.nisc.gov. The value for water, H2O, condensed phase, search, and delta H formation of liquid water is negative 285. Okay? Yeah, you're gonna need to put that in. Let's go ahead and take a screenshot of that. I'll put the screenshot over here. There it is. For water, so the value for water is how much? Negative 285.83. Liquid water, negative 285.83. Okay. So what should be the standard enthalpy of formation of our hydrate? So this is negative 285.83. And there's 7 moles here, okay? So I want to know what this is. This is delta H formation of the hydrate. Let's call that X, okay? So we have everything we need, right? We got products minus reactants should be equal to 133 kilojoules, right? So what would this be? Okay. So I'm gonna say delta H formation of magnesium sulfate solid plus 7 times the delta H 1 times there, plus 7 times the delta H formation of liquid water minus delta H formation of the hydrate is equal to the delta H of the reaction, which is 133. So this is 133. This is 7 times negative 285.83. And this is 1 times negative 1261.79. Yeah, the negative of these minus these, right? So minus, so this is going to be minus 1 times the delta H formation of the anhydrous salt plus minus 7 times the delta H formation of water let's see, plus yeah, the negative of these, you add that to 133, that would give you minus, no, minus delta H reaction, right? Delta H reaction minus,
133 minus those two divided by negative.
okay, so it's this one minus that one. Okay. So it's not minus, so this is gonna be this one, magnesium sulfate plus water minus the experimental delta H of reaction, which was 133, right? Enthalpy of dehydration. So that minus the delta H of dehydration of the hydrate. Is that right? Okay, so minus 3395 kilojoules per mole. Okay, let's try it again. This is the 133. So it's going to start off with this 133. No.
Yeah, you could do it that way. I did 133 minus the water minus the magnesium, and then I divided by negative 1.
Well, 133 should be minus because you want to make this positive, right? So you want to move this to the right and you move this to the left.
I just divided by negative 1. Like multiplied by negative.
Yeah. Okay. So I'm going to go delta A. Delta H formation of the products minus the delta H overall will give you the delta H of the reactant, right? So sulfate plus 7. So it's going to be equal to delta H formation of magnesium sulfate, okay, times 1 plus delta H formation of water per mole times 7 moles of water minus the overall delta H, which is, where's the 133? Oh, right there. It should be negative 3395 kilojoules per mole. Okay? And so what does that mean? What's that reaction? Actually, it's magnesium solid plus H2, okay, gas plus sulfur solid plus oxygen gas gives you magnesium sulfate dot 7 H2O solid. Okay, so your hydrogen, you get 14, so that's 7 right there. Sulfur, you have 1. How many oxygens do you have? 4 plus 7, that's 11. So that's 11 over 2 oxygens. Okay, so this is the delta H formation of magnesium sulfate heptahydrate. Okay, so now we have that. Let's compare that with the literature value. Can you find the literature value? The only place I've found it, I've looked at webbook, I couldn't find it. CoData website, couldn't find it. I did find it in Lang's handbook. So here, go look for it. Right there. If you have an electronic copy of Lang's handbook, you can look for it there too. So I'm gonna pause this recording until you find it. So what's the correct value? Wow, 0.7? I got very accurate results, huh? And so equals, percent error would be what? Standard experimental value based on the experimental data you got minus the literature value divided by the literature value times 100%. 0.2% error. Huh? That was your group? No, I was using Jasmine's numbers here.
No,
you're in the same group?
Well, no, they had the glare, so they had to.
Oh, they're using your, okay.
Yeah, our video was
0.2% error. Well, you have a research grade equipment there. It's old, but it's research grade, so. Okay, so that's it. Percent error?